So we are going to go a little deeper into single displacement reactions. So far, we've just focused on identifying them, but now we're going to consider situations where you have the reactants, but you don't know what the products are going to be, and we have to make those predictions. We're actually going to be doing this with both single and double displacement, and we're going to break that into two smaller quizzes. So our next quiz, probably mid next week, is going to be over single displacement reactions, predicting the products. So we're going to be following these steps. I won't read them to you now, but they are listed on page 37. It is worth you checking those out because if you skip one of these, it can have an impact, but I'll walk you through how to do these in the examples. So let's get right into it here. Consider this first example where we have these reactants. We have silver nitrate, which is actually one of the solutions we're going to be working with in tomorrow's lab here. It's this gray stuff. And we are going to put a strip of copper into it, and we're going to see what happens. You can also predict what happens on paper if you know how to do that. So let's take a crack at it here. First thing I recommend doing is looking up the charges of all these ions involved in this equation. And silver has a +1 charge. I like to write the charge just on top of it. Why don't you do that with me, please? Nitrate has a charge, I believe, of -1. Yep. Write that over there. And that explains why there are no subscripts there, because they neutralize each other as is. And copper, this is kind of an important thing to note. Copper could have a couple different charges here. It could be +1 or +2. The assumption we're always going to make, and this is true like 70-80% of the time, we're always going to assume the higher charge on an element like this. So in the case of copper, the highest charge it could have is +2. So that's going to be our assumption. When we don't know what the charge is, we're going to assume that it's the highest charge. Make sense? Okay. Now, the first question we have to ask ourselves, and we haven't done this yet, is we're going to ask, will a reaction happen at all? Is there going to be any change, or is the copper just going to sit there in the silver nitrate and do nothing? That is a possibility. The way we answer that question is to look at something on the back of your periodic table called the metal reactivity table. You'll sometimes see this called the activity series. So flip your periodic table over if you haven't already done that. And look for the column labeled metal reactivity. So think of this as a ranking of the most attractive or most appealing cations. All right. So the supermodel of the cation world is lithium. Okay. It's the dance partner that everyone wants, to use that analogy that I've been using, okay? The least appealing of the cations, paradoxically perhaps, is gold, okay? No one wants to dance with gold, ironically. You'd think it'd be very popular, okay? And then we have rankings all the way, everything in between. So in this case, we're interested in, the two cations that we're interested in are silver and copper, and we want to know which is going to be most appealing to the anion nitrate. Who doesn't want to dance with more? Can you guys tell me which one is higher up on the list? Copper is, okay? So indeed, copper is going to steal silver's dance partner. So let's go ahead and write that in here. I'm going to leave a little bit of space here in case I need to add some subscripts. So copper has a charge, we know up here, of +2, and nitrate has a charge of -1. So what am I going to have to do to this formula to neutralize it? You guys following me here? If copper has a +2 charge and nitrate has a -1 charge, how do I neutralize the formula? They don't currently cancel each other out. I need 2 nitrates. Yep, so I got to put that in parentheses. This, by the way, is going to be aqueous. That means it's dissolved in water. Don't worry about how you know that at this point. Just take my word for it. And then by itself, we have the broken-hearted silver in this case, all right? Silver leaves the dance alone, and it's also going to be aqueous. So what did we just do here? Because I want you to kind of know the steps. Step 1 from page 37, we looked at the activity series and determined if a reaction is going to happen. And since copper is higher up on the activity series, there is going to be a reaction. There's going to be a switch. There's going to be a dance partner stolen. All right. So then we go ahead and do the switch. Step 2, we neutralize the compound if necessary. It was necessary in this case. And lastly, only after neutralizing the compound, we need to balance the equation. Those are two separate things. So we're going to check our numbers on the two sides. And here you see we've got 2 nitrates on the right side. So I'm going to need to put a 2 coefficient here. Remember, we can only use coefficients to balance the equation. We never use subscripts for that. And how about everything else? I think everything else is balanced. So that's all we needed. Any questions about that? All right, why don't you guys try the example? Anyone listening to the video here, you're probably going to want to fast forward it. Okay, let's go over the U-try here. If you have a question, let me know. Step 1, we determine if a reaction is going to happen. Who is more appealing to the anion here? And the anion is SO3 with a -2 charge. Magnesium has a +2 charge, and iron has, in this case, it must have a +3 charge. I know that by looking at the charge of the sulfate and knowing that they have to be neutralized here. We could do a T chart for that if you wanted to. All right, so we look at our list and compare magnesium to iron. Which is more appealing to the anion? Magnesium. Okay, that means a switch is going to happen. So let's go ahead and make the switch. So magnesium is going to come over and bump iron out and steal iron's dance partner. So we're going to have magnesium sulfate. It's going to be aqueous. Leave a little space in case you need to add subscripts. And that is going to leave poor iron by itself. And that's going to be aqueous iron as well. Okay, now I consider if I need to add subscripts to magnesium sulfate. Magnesium is +2, sulfate is -2. So do I need to do anything to it to neutralize it? Nope, it is neutral. Nothing needs to be added. Last step, using coefficients only. I'm going to now balance this. So the thing that I notice first is the iron. I've got 2 on the left. So I'm going to put a 2 over here. I also have 3 sulfates on the left, so I'm going to put a 3 right here. That creates an imbalance of magnesiums, so I need to come back and put a 3 here, and now it is balanced. You guys have any questions about how I did that there? Okay, last example, and this one isn't in your booklet, but you can write it down. It's a quick one. Just wanted you guys to be aware of this scenario, because you're going to see 1 or 2 of these. We have silver nitrate up here, again, reacting with gold. You guys recall what I said about gold? It is the least appealing of all the cations, okay? So nothing happens here. The nitrate looks at gold, and again, paradoxically, is like, nah, I'm good. I'm going to stay with my dance partner. Okay, so no reaction happens. They just sit there. No bubbles form. No heat is released. No new smells. No new colors. No chemical reaction is going to happen when you mix these two, because no one wants to be with gold. All right. Any questions about that? All right, you guys got a little time to start your practice assignment. We're going to have more time tomorrow. We're also going to do our lab. Thank you for your attention. Yeah.